Welcome to General Chemistry Mini Lecture Series, Lecture 29, Heat Stoichiometry. Let's go over enthalpy change, delta H of reaction. That's simply the amount of heat involved in a chemical reaction under constant pressure conditions. And the delta H of reaction values, they are measured experimentally. Negative values means exothermic reactions giving off energy or heat. Positive values means endothermic reactions, absorbing heat or receiving the energy from surroundings. Delta H of reaction values change sign when a process is reversed. For example, carbon reacting with oxygen forming carbon dioxide, the delta H is negative 393.5 kilojoules. Then the reverse reaction from CO2 to carbon and oxygen, the values are still the same, but the sign is changed. Delta H of reaction is an extensive property. What does it mean? It means when a reaction is multiplied by a factor, then you have to do the same for the delta H of reaction. Okay? For example, the same reaction we talked about above, for this reaction, the delta H value is negative 393.5 kilojoules. And now, if we multiply this reaction, the first reaction, by 2 carbon, 2 oxygen, 1 times 2, then 2 carbon dioxide. But we have to do the same for delta H. 2 times negative this value, and it gives us negative 787.0 kilojoules. Thermochemical equations. This is a combustion of propane. In thermochemical reaction, you have one more component indicating the heat either released in this case or absorbed in other cases. The first part is just the traditional chemical reaction. You have reactants on the left-hand side, you have products on the right-hand side, and it has to be balanced, have to have the phase indicators. But you see, in addition to this traditional, conventional chemical reaction, we have another component here. So that's the heat. And this is the most common way of writing the combustion of propane. Less common way will be still the same reaction, but instead of writing delta H equals negative 2044 kilojoules, we just treat heat as a product. And the least common way, they still write the conventional chemical reaction, and then they will indicate this is exothermic, 2044 kilojoules release. Okay, all of those three ways, that's fine, but most common you should see is the first one. Endothermic reaction, let's take a look at the photosynthesis of glucose. The most common way, you have the reaction and then positive value. Positive means the system or the reaction gains energy. Less common way, this is heat added to the system, or in other words, the heat is treated as a reactant. So therefore, you write the heat as a reactant. And then the least common way, again, you write this conventional chemical reaction, and then you say it's endothermic, 2808 kilojoules heat needed. Heat stoichiometry. Let's take a look at this reaction. That's a propane reacting with oxygen. Delta H is negative, which means it's an exothermic reaction, gives off heat. We already learned previously, this tells us 1 mole of propane is equivalent to 5 moles of oxygen, 3 moles of CO2, 4 moles of water. That's what this part tells us. Now, we added this heat part, then we can further say 1 mole of propane is equivalent to negative 2044 kilojoules. Those are the relationships in heat stoichiometry. We can also say that the delta H of reaction for 1 mole of propane, you see the coefficient is 1, is negative 2044 kilojoules. And then you see we can write conversion factors based on this relationship. If we are converting from moles to heat, we can write down 1 mole on bottom and then the heat quantity on top. Or if we need to convert from heat to moles, we do the opposite. You see we have another reactant. We can also say that H reaction for 5 moles of oxygen is negative 2044 kilojoules. And we can write 2 different conversion factors for this relationship. And further, the same way, you can write conversion factors between CO2 and heat, also between water and heat. That's why we call that heat stoichiometry. In addition to the conventional stoichiometry, now we have the heat part. This is the conventional stoichiometry we already learned previously. Now we just add heat into it. Everything else is still the same. And now we can perform calculations related with heat. There are so many calculations can be carried out using those relationships. For example, we can convert from the heat of substance A to the moles of substance A, then from moles of A to moles of B, and then from moles of B, we can convert that to the mass of B or the particles of B. Let's use this example to digest what we just learned. Calculate the heat evolved in the complete combustion of 5.28 kilograms of propane. That's the same chemical reaction we just talked about. What do we know? We know the mass of propane, and we also know the relationship between the moles of propane and the heat. We get that from this balanced chemical reaction. 1 mole of propane is equivalent to negative 2044 kilojoules. So now things become easier. We just need to find out the heat in kilojoules. So first, we know the kilograms. We should convert that to grams, and then further convert from grams to moles, and then using this relationship to kilojoules. Here are the relationships. Let's solve it. Start from what we know, 5.28 kilograms of propane. From kilograms to grams, kilogram on bottom, gram on top. And now from gram to moles, place grams on bottom, moles on top using the molar mass. And now we need to convert from moles to heat using this relationship. Moles on bottom, heat on top. You see? 3-step calculation. Bingo, we get the job done, taking care of the sig figs. So this is the answer. Example 2. We have this chemical reaction. Now if 1.15 times 10 to the 5th kilojoules of heat is released, how many kilograms of oxygen gas is produced? We know the heat and we know the relationship between the mole of oxygen and the heat of reaction. So we need to find out the mass in kilograms. And now, since we know kilojoules, we start from kilojoules first, then convert that to moles, then from moles to grams, then from grams to kilograms. This example 2 is just the opposite of example 1 in terms of the calculation strategy. Here are the relationships can be found in this question. Start with what we know. We know the heat is 1.15. And why is negative? Because it says that heat is released. If it's released, it has to be negative. That's kilojoules. We want to convert that to moles, okay, using this relationship. Converting from kilojoules, place that on top, bottom. This negative 196.1 on bottom to 1 mole of oxygen. Okay, you see that's 1 mole here. Kilojoules are gone, and we need to convert from moles of oxygen to grams of oxygen using the molar mass as the conversion factor. Moles oxygen are cancelled. Now we have grams of oxygen. We need to convert from grams of oxygen to kilograms of oxygen. And now take care of the sig figs, 10.6 kilograms of oxygen. That should be the correct answer for example 2. Those are the end of lecture 29 quiz questions. I will work on number 3 with you guys together. According to the following thermochemical equation, how much heat in kilojoules is released by burning 88.2 grams of propane? According to this chemical reaction, we start from what we know. We know 88.2 grams, and then we'll convert from grams to moles. Then the next step, converting from moles to kilojoules using this conversion factor. 1 mole of propane is equivalent to negative 2044 kilojoules, and that should give us negative 4088 kilojoules. That's the answer for quiz number 3. I will see you guys in lecture 30.